Well, thank you for joining us again today, and thank you also to WSP and our guest speaker, who we'll introduce shortly. Today's webinar, it is about 3D GPR and the assessment of the Tay Road Bridge. Really looking forward to this one, by the way. Really excellent presentation, and we really hope that you get some value from this presentation. A little bit about Zoom and the webinar format. We all know this stuff, but there's individual things each time you attend one. One of them here is that everyone's muted, apart from the presenters, of course. And if you want to ask questions, then put them in the Q&A window. We'll try and answer these questions. We have some panelists, of course, from Kontur, and we'll try and respond to you where we can. And if we pick up on it, I'll act as a bit of a middleman today, and I'll try and answer them live and ask questions with our presenter today and get them answered during the webinar as well, right? But if we don't get to those, we have a log of them, and we'll come back to them offline and answer them for you, all right? Okay. All the questions and answers are visible to all participants. So today we have Dr. Michael Gordon, Technical Director from WSP. Michael has worked in the pavement industry for 20-something years, has a wide range of expertise in UK design, maintenance, and investigation projects. Currently leads a team that undertakes research projects for Transport Scotland. You might already know me. I'll be host today, but I'm the Kontur Technical Sales Engineer, and you may have spoken to me already, but I will be the host today and try and extract some of the questions and things that you're posting in the Q&A box. So with that intro completed, let's hand over the controls to Michael, and he can begin his presentation. I'm going to stop sharing, and you're welcome to take control.
Thanks very much.
You're welcome.
Hopefully you can hear me okay. This is, sorry, being very clever. 3 screens, not clever enough. Forget the share. Thanks so much, Paul, for allowing me to have a chat about this particular project. I'm going to just do a small introduction to ground penetrating radar, just for those who are unfamiliar. I'm sure the vast majority in this call will be. Just want to fill that in. Then I'll talk about the Tay Road Bridge in a wee bit more detail, hopefully, and have some conclusions. And then I know it's open then for some questions. What is ground penetrating radar? Peter Annan, an absolute wizard of ground penetrating radar, puts it down in a really simple. GPR uses electromagnetic fields to probe lossy dielectric materials to detect structures and changes in materials within properties. And basically what it's doing in a really simple way is it pulses. I'll just show you in a nice simple way. It's a pulse of electromagnetic wave is pulsed into the material that you're reviewing. And what happens? You get a sequence in the old systems now, like a time signature. This is me describing how an impulse system works. This is different to what Kontur has. But basically, it pulses into it, and then what happens is, as it changes, the electrical property changes, it's experiencing change. You get a reflection back, and that could be a boundary. And it's all recorded in frequency. It's then switched into time. There's various equations. They're all based on Maxwell's equations, but in a simple way, you're able to sort of run these. And I'll just show you in a simple process. So pulse comes in, experiences a change in dielectric. It records as a signal. And then another pulse comes in, changes the dielectric, and then a pulse. Now this is this is based on the impulse radar system. The step frequency is slightly different. So I just made it in a really simple way to try and help us to understand. Normally, the information that we see can be shown in several different ways. So you can have A scans, which looks like, if you remember the old days of physics, your oscilloscope. So again, these are all simplified. What's going on is more complicated than this, but an A scan is a simple scan of the data that comes through. Then you've got a B scan. So you imagine if we take this B scan, this is made up of lots of these waves. You take this wave and you imagine you're tilted. It's now pointing into the ground, and then it's color coded up. So the higher that peak is, If it's positive, it might be a darker color. And if it's negative, a whiter color in this particular image. And you can see when you start to put these together, you start to see a picture. It starts to make a little bit of sense. For those of us in the trained eye, this was taken to the surface, and we can see some sort of a structure in the road. And to others, it might look stranger. Then we've got these C scans. Now, this is what's changed. So in the old days, when I was doing it when I was doing my PhD, I looked at it, and it was all, you could do these, but not as well. Nowadays, the technology is so much more improved. And these new, you can do this with a single scan antenna, but these new three-dimensional array antennas make this even more fun. And this is the stuff that that we've come, and this is what I'll delve into when I look at this project in a wee bit of detail. Okay, so you have a C scan. So listen, one of the things I want to do is understand consultant engineer, we've used a lot of different machines. And I just want to show, okay, these are some of the machines I've used in the past. So, and then we'll talk a bit about the Kontur system. So some of you will be on the call and you'll recognize this stuff and you'll go, yep. Maybe some of you will say the manufacturers and you'll recognize. So here we've got an Opera Duo. The top one is an Opera Duo. It's IDS. Again, it's a utility scan. It's a dipole system. So you have two things. You have a dipole ground coupled, and then you've got the air launch. Again, this is just another company. IDSs do this. Then we've got some other companies here. So here's another one. This is JSI's range. These are a wee bit old. Some of the older machines. Antennas again. Key thing is look at this one. It's a single scan, central frequency 900 megahertz, 400 megahertz. When we're thinking about these numbers, what are we thinking about? We're thinking about the lower those numbers are, the lower that frequency is, the more it penetrates, but it doesn't resolve those thin layers. So, for example, if somebody says to you, "Listen, I've got really thin material here. It's in your term might be an inch material. I want to look at that, or millimeters, something like that." And I want to look at that. Then these antennas, these higher frequencies, see this number here is 2.6 gigahertz. They come into handy. Now, I'm going to take you into a place where the Kontur system is sweeping all these frequencies, which makes it a wee bit exciting. It's such an amazing thing when we look at it. But these all have, when I compare each machine, each one has its pros and cons. Each type, we're not talking about the actual manufacturer, we're talking about the signal. Is it an impulse signal or is it a step frequency? So this is again this is their air launch machine. Okay, so air launch is different, ground coupled. The amazing thing about ground coupled, you get way more energy into the ground, because the minute you lift that antenna off the ground, you start to lose. Because what happens, you've got the signal going through the air and then into the ground, you get losses. Coupled, but you know what? When you're moving at speed and stuff, there is advantages to air launch, and there's a lot of work's done. You haven't got this rig that's just quite hanging above the road, it's bouncing on things. These air launches have their own. So if the combination of air launched ground couples is good. Okay, so let's have a look now. So these are impulse systems, and there's loads of companies. I could list loads of companies that do this, and you'll all know other companies that are famous and they've done a lot of work. Look at the difference, and this is just a simple slide. Where the difference? So there you've got the impulse radar system I've just shown you on the right. Now you've got the step frequency system, okay, and it works in a different way. And some of those of you, the mathematics behind it, IFFT, frequency. So you're working in the frequency domain, and you flick it into the time domain. The pulse system is all coming in time windows, okay, and then one stacking. Sometimes you can stack the stuff up, you have to. Some is integration in time. Okay, and there is a difference, and there's a power between each one. So let's have a look in this is the system in the Kontur system. All this information comes into their software package called Examiner, and it's a great package. It does a great job. I find it really helpful. It really made my life easy compared to, I think, the old days when I used to process it with MATLAB all my life, and that was in the 90s, so it's a nightmare. But anyway, it's a really powerful piece of software. But no matter what system you're using, the key here is the software. Now, what I find about their software, 3D radar software, it's really easy to use. It's very well written. It can move, it can deal with a lot of data very easily. And that's what I find really helpful, especially when I show you the case study. Okay, and again, you'll have your own piece of software that you may set to, and that's what makes the difference. What we find, especially for us, your process and stuff, we want something that works really quickly, and you can quickly get the results. It does take time, and you think about nowadays. Imagine if we go back, it used to be a single channel. It'd be so. Can you imagine now? These or like 26 channels. Each one is gathering all this information. Those produce ginormous files, gigabytes of data, and that's where the processing software is absolutely key. And I know for some reason that this, well, you've taken that and you've developed your own stuff. But again, Examiner does a really good job on this one.
Michael,
here we can see that. Yes.
Would you mind just popping your microphone just a tiny bit down? That's it. Yeah, there we go.
Is it not catching it? Is that better?
I think it's the noise cancelling.
Oh, right. It's probably because of all the noise. That's a bit better now. Hopefully that's a wee bit better.
Perfect. Thanks, buddy.
Yeah, no problem at all. So understandably, this is just the setup. You've got the antenna itself, and then you've got the acquisition box, which is the brains on the Kontur system. So this is called the Geoscope Mark IV. They're probably working on the Mark V. They maybe have a Mark VI as well. But this is the Mark IV. I think this is the latest model. Key things, and we're all doing the same. RTK corrected. You can resolve down to in 15 centimeters, whatever the equation, the conversion into inches. Very high accuracy. That is usually a paid system, but gives very high accuracy position information, and that is absolutely brilliant. So previously, we would have always relied on the survey wheel, and the survey wheel is there. So there is a survey wheel you can have, but it's a combination between the survey wheel information getting fed in and the RTK system. Now, we all know, and I've been on jobs where it is a challenge with some jobs where you might have issues with the RTK. That's where the survey wheel comes in. I was on a job in Orkney in Scotland, and it's so frustrating. Halfway across this bridge, in the middle of nowhere, the the ticker system I was using had no 3D data. The GPS data just stopped working, and it was because it was so reliant on the mobile phone signal. So we got half across the wood, and it stopped working. Thankfully, again, the survey wheel helped us with that one. So these are, and again, it's a great system, really simple, very powerful into the PC and in the processing stuff. And as I said, the processing of this software is undertaken through their Examiner system. Some people might say it's a wee bit expensive, but you know what? It's worth its weight in gold. Great team of people working in there, and it's good. And you'll find the same with whatever software you're using. You think of all the work that's going into these software, whatever, there's a lot going on. Here's just to show you one of the systems. Apologies, it's a wee bit small. This is if I can get this right, this is the ground coupled antennas. Is that right?
That's right. Yeah, that's right.
Yeah. Yep. So there is a coding. Okay, so there is a little codes in here that means something. So sorry, it's so small, but basically, in fact, what I'll do, let's just zoom in. Yeah, we can do that. Yeah, that's good. Okay, so the code, and you can see it says 09. So that's ground coupled G09, and that tells us it's 900 meters, 0.9 meters wide. And you can see you go from 0.9 right up to 2.4 meters. Pretty good, especially when we do carriageways, decks. You want that. And then this just gives you the guidance number of channels, and you can go right up to 28 channels. Again, so really good. The more channels, the better, but a lot of data coming in. One of the things you have to think about when you're using these systems, and I learned the hard way, is the dwell time. Now, I know Jacopo's on this, and there's other experts. That was something Jacopo had to get into my head. Jacopo works for Kontur. He was saying, Michael, you've got to remember, don't think of just driving really fast across these bridge decks. You've got to think of the dwell time, the time which it's pico. Let's get this right. Help me in this. Is it picoseconds it's measured in? I believe pico, is it? Am I right in saying that?
Microseconds, actually.
Oh, it's microseconds. Okay.
It's microseconds, yeah. Yep.
Okay. I thought it was picoseconds. I'm sure Jacopo will write something if we got that wrong. But basically, each point has to dwell for a certain time. If you're driving too fast, you get blur in the data. You have to be careful. And the great thing is the system warns you. It says to you, it'll start beeping if you're not at the right. So you've got to get the dwell time. But it's as it's pulsing, it needs to spend a certain time. If you drive too quickly, we learned that. You can learn that the hard way, especially in some of these. But it's all very good. So that's basically the system. So that's the ground coupled. And this is sort of the data you can get. And you can see, just a quick summary, you can see it resolving. So this is the surface of the road, and this is rebar in some concrete bridge deck or whatever. And here it's resolving the individual reinforcing bars. These are producing miniature hyperbola, the mathematical shapes, just the way the maths work. And here you can see it picking up individually the position of the rebar. Now, there is a difference. Can you imagine in this? Some of you look at this and think, if you experience this, the bow tie antennas, these impulse radar systems, they have an advantage because they can resolve it much more. Instead of having the sample rate here might be, I think it's 9 centimeters. I think it's 9. Paul, am I right in saying that 9 centimeters between each scan is the minimum you can get?
So the antennas are separated by 7.5 centimeters.
7.5.
Yeah.
Okay.
And then the trigger spacing is user defined. So that can be from 1 centimeter up to many meters. But in most cases, in a lot of user cases, if you're experienced in creating grids, for example, laying them out on the ground, most people go for a square type grid setup, right? So they'll mimic the channel spacing layout. So they'll go with a 7.5 centimeter by 7.5 centimeter grid, right? But in these kinds of cases, and I'm pretty sure you're gonna take us on this journey, is that you could choose a finer, more regular or more closely spaced triggers to capture more detail if you wanted to. So it's user defined. It's not a black box solution. It's not something you just turn on and it happens, right? It's user defined.
Brilliant. And I think when I was doing the work, when we do the case study, I was working with about 9 centimeters. You'll see in the data, I'll show you in the data, but it's good to hear you can tighten that up. But again, remember, there is this draw between, because you have to be careful, because if you get it wrong, just to do with the mathematics, it can start to cause a bit of issue. And I remember the great thing about it is what I found was I was on the phone call per Jacopo. I was phoning them all the time when I was trying to just get it right. He kept it right, and their technical team are really good. And Paul keeps you right, So make sure you have Paul or Jacopo's number. It's always very handy, especially absolutely. So then we've got they're like a V-shaped antenna. So we're looking at the plan view. And this is now their air launch systems. And let's have a look at them. You can see the widths of them go from 0.9, but they go even wider. Now you can see at 3.3, pretty wide, great in the airfields. Maybe a wee bit, we have to be careful. Certain countries have limits to how wide you can go, but 3.3 is really good. Standard widths, for example, in the UK, 3.5 meters. So this is a good antenna. This is very wide. We didn't use that. We stuck to 2.1. But again, these are air launch different. I'm going to show you some data from them just to show you what the difference is. Again, you can see that the number of channels goes from 9 individual channels, pointing in both directions, both orientations. Very interesting about that. How you can resolve, it's a great thing. Goes from 9 up to 41. That's a lot of channels. Again, as I say, the project I had both. Very fortunate, I had both the air launch system and the ground coupled system, not run at the same time, separately from the same unit. Great setup. Again, we were very fortunate to have that. So this is the type of data from the air launch system. And again, you can see the difference. Here's it's a bridge deck again, doing some work. And here you've got the direct wave. See, this is very strange what's going on here. The orange is the surface of the road. If you're on a bridge. You've now got this line above. That line above is the direct air waves going between the antennas. You separate that out again, and then you're looking at that, and it's really good because it works in a different way. Okay, so you can't resolve the rebar as well, but it works in other advantages. I mean, this antenna, and I'll try and show you some of the slices that these things can do, is amazing. So you can basically do a CT scan right through the deck, and this is where they come in through. And I'll try and show you some video of that process. So there's the two antennas. You can see there the ground couple is very much flatter antenna, and then you can see the V notch. You see that V notch in the air launch. Two different. And we were very fortunate in this project. We had both, which was really good for that. And you can see the shapes, the way the positions, as Paul's spoken about. You've got the ground couple system, the way the antennas point slightly different, point in a different way compared to the V notch. Just the way the antennas are laid out. This is sort of the mathematical equation. And this one is the DX18, for example. So again, that would stand for DX. This is the old, I think it's still called DX, maybe called something else. So 18 would be 1.8 meters wide, okay, 21 channels. Now remember, 1.8 meters wide means that effectively, just to do with spacing, it measures, I think, 1.5 meters. Let me just check that number. Let's have a look at that one. So we go back into this slide. Someone should tell you. It's not very helpful. It didn't. So you see this, look carefully. So in that antenna, 1.8 meter wide, but the effective width of what it's scanned is 1.6. So remember that when you've got to get that overlap. You know, something to take into, we have to take consideration. There's always just the way it's manufactured, totally understandable. Again, the antennas are remarkably light for what they are, which is great. You know, they're not really heavy. And again, it's important to have a proper rig. And I'll show you just a wee bit of that in the case study when we talk about that. Okay, we've gone through that. Let's look at the case study. Well, let's get into the meat. This is the bit which it will hopefully key facts. Let's have a look. Oops, apologies for that.
Nice.
So yeah, that's just a wee side thing. It shouldn't be in there, but we'll worry about that. Key bridge is 2.2 kilometers long. Okay, so probably about whatever that is in miles, that 1.8 to 1.7 miles long, and it was over the Tay River Bridge, the River Tay, which is in Scotland, just north of Edinburgh, in a place called Dundee. So very, very important bridge. Again, it was designed by William Fairhurst, built in 1963 and then completed in 1966. And in those days, the cost was 4.8 million. I don't know what the exchange rate is now, but it wasn't cheap, but a great thing. For those of you who are the structure engineers, you'll know this is 42 spans, 55 meters in length, increasing up to about 76 meters. And then there's navigation spans as well. And again, my background is not structures, but I had to speak a lot to the structures friends about this, but it was a fascinating, here's the more amazing thing. It's made of hot road asphalt material description, but it's blended with Trinidad Lake asphalt. And this is what created this amazing material. The material is still on the bridge deck. There's been surface dressing, which is coated chipping's gone on, but the original material is still there. It is amazing material. Understandably, the reason for this project is we need to have a look at it, and they're looking to replace it. So that was the reason. So we had to measure it on very thin layers, which again, this machine was able to do. Just to give you some background, let me just zoom in and just show you. This is some of the construction that you see. These are from the 1960s photographs. Just get some idea of the decks, and sort of pins, and the way the shear bolts were. Sorry, I can't explain to you exactly what's going on, but I'm sure those here you understand the structures and the build will understand it better than me. Again, you can see it gradually working out. It's an amazing project. You can see the reel systems for laying material, and this is then building up the piers. Just keep going. I've got a few photographs, so hopefully they'll be. Again, you can see these amazing pier columns going up. These are some of the navigation spans. You need a system for bringing up the beams. And again, you can see it all being built up, gradually building up the whole road network to join it all. So it was all amazing. Yeah, more stuff. You can see then there was a toll booth here. So you used to charge feet going across it. Keep note of that. I'm going to bring that up later on. Just some stuff that was amazing that the system found. Again, this is the connecting sort of road network. And again, there was this area which is a platform above. Parts of these have been removed. They're no longer there, but they used to bolt down into it. So it was like a viewing platform, but over time, that's literally above the booth and stuff further down in the middle as well. So let's talk about the system. A company called PTS, based here over in the UK, brought them in. They had a machine, so we brought them in to undertake the work and then process the data. And as I said, 2 machines were used, and they're launched. You can see the V notch, and this one's just get right in there so you can clearly see what's going on. Now, key thing is this. Now, watch this. One of the key things you want to do is try and keep that device from bouncing. And you can see the PTS have stability here. They've got these aluminium. You want to make this as light as possible. You can see the bar, the connecting systems. Okay, so you've got to try and stop that thing from bouncing, because that bouncing effect can also have a slight interference. You have to be careful. Again, survey was done very slow, 20 mile an hour, 25 mile an hour. We were lucky. We had a traffic management system, a large vehicle with arrows pointing to slow everybody down. The bridge team were really helpful. So that's that one. Then you can see the difference now in the ground couple. Smaller antenna, again. But you can see it's coupled to the ground wheels. Again, we don't want to go too fast because we don't want that thing bouncing. Also, we've got the dwell time, so we have to be careful of that. And the spacing that we'd set up in the system that we would scan. In this particular case, it was scanning every, I think, about 8 or 9 centimeters. Okay, so that's why you'll see the reinforcement will look a wee bit closer. But that's what we were doing, just to do with. So again, you can see the rig. Again, you don't want to be doing too fast. You don't want this to be bouncing. You want to get all the energy. You can see it's just hanging above the deck. You want to get as much of that energy into the material you're scanning. And that's the key here. And it makes it much easier. Okay, so key things are 2 lanes each direction. We ended up doing 2 scans with this machine because it's wider. I think there was 3 scans per lane for this one, both directions. There was a lot. The data was massive, gigs and gigs of data. Again, the advice always is when it comes to have an examiner, which is the only actually system that can process all the data, you need to make sure you've got a good, powerful machine. It needs to be an i7, up to date, fast. You want to have a solid state hard drive, lots of terabytes of memory. And it's fine. You can get these things, but the ideal machine. I remember Jakob used to say to me would be like a gaming machine. But you don't have to. Something that's got powerful, good graphic chips really makes your life easy. I don't. I've got an HP like a business. It was not. You don't. When you've got older machines, it's a wee bit slower. But understandably, it's processing lots of data. It's really good. So again, as we said, air coupled had 25 individual channels, and it was about 1.875 meters. And ground couple, smaller one, 0.9, 12 individual channels, and then that's the space in 75 minutes. Okay, so what we wanted to do, understandably, when you're doing any radar survey, you want to calibrate. You want to get that calibration information. So I processed both data, and one of the big challenges I had was there was a team coming in to have a closer look, and I'm going to show you. They wanted to clean into the deck, into the asphalt. But the care is they didn't want to touch the concrete. You don't want to damage the concrete. So we wanted to use radar to resolve extremely thin layers. The layers got really thin. So let me just show you how thin this is. You can see the inches. You can see, in some cases it's about 2 inches. This is what you can see is here's the HRA. It's defined material. There was a wee bit of waterproofing involved in it, and there's tar and different things. And this one was actually a wee bit thicker, but it's only, look how thin this is, just over 2 inches. And this radar system was resolving just over 2 inches. Absolutely amazing. Great to see this. I would have loved this years ago when I was doing my PhD, but that's another story. So you can see it's about just over 2 inches, 2 and a bit inches.
Yeah, and this comes from the upper part of the spectrum. The higher frequency part of the bandwidth. Where you can resolve really fine near surface details. Yeah.
So there's something I didn't say to you is this: the step frequency sweeps. Now, here's something I forgot to tell you. If I remember, we talked about the central frequency of the impulse system's 900. The amazing thing about the step frequency radar is it sweeps from 3 gigahertz, 3,000 megahertz, down to about 500 megahertz. So as Paul's saying, is 300 megahertz maybe?
No, it's actually 100, but we say 150 because of different variations in the actual geoscope itself is incredibly powerful, but due to regulations in different parts of the world, then we have certain low end and high end cuts. Okay, so 150 really is a typical low end cutoff. Really, so it's the entire bandwidth with no central frequency. Step frequency has a lot of advantages here because you can resolve very fine details near surface, but also resolve and keep the resolution as you increase in depth as well. So small object detection and retain that resolution regardless as you slowly move into more of a depth volume. Okay, where the lower frequencies start to come in, you retain that resolution. So it gives you a good optimized system. Yeah.
No, for me as an end user, it's brilliant because in other systems you would have to have a low frequency antenna and a high frequency antenna. So you'd have to do multiple runs. If you think about it, this is doing it in one go. That now is an advantage. So in one scan, it's looking at the thin, very close to the surface, deeper down. Now I know in the bridge deck, it's not too thick. So we're really reliant on those high frequencies resolving, and I'll show you the data. And again, I've been doing radar for a long time, since about 1996. And I haven't seen data like this. Okay, some people in this call might have seen data, but this is good data. But the machine does some amazing stuff. This is another row core. So just so you know what's going on, we were taking samples. We needed to take some cores from the bridge deck to calibrate out the radar. And this is what helped me. This was another core. Again, very thin. It's only just over 2 inches. Really thin material. And this data was being resolved by the system. So let me just I'm going to take you into, we're going to look a wee bit closer at data now. I've talked about, let's have a look at the data, because that's what you want. Sorry, this is a pretty old drawing, okay, and I want to show you something that's going on. So here we've got the bridge deck. This is the cross section. Just going to zoom in on this particular section. Hope this makes sense. Let's get in a wee bit tighter, just in case it's not coming up here. So here you can see, so in the old drawings done in the 1960s, we get a sort of indication what's going on. There's a lot going on here. There's a lot going on. I don't understand half the stuff. Those are structural engineers, it's called, on the exactly what's going on. There was some sort of bolts. You see there's a gantry. So what you imagine, underneath there's a gantry, so the teams can get underneath the bridge. It's on a reel and it hangs off, but it was bolted into and the actual bolts themselves are just below the surface. There's a wee notch. We're going to have a wee look at this, what the data was showing. Okay, so let's come back. So I'm going to look at this, see, here's hoping this works. I think this should show. So now what you're going to see, this is the scans, okay, with the one antennas, and I think this is, I believe this is the ground coupled antenna, okay. I'm hoping this is going to work. I'm going to click this, and what we're going to see is a slice. We're going to go like a scan, like an MR scan. We're going to go through the deck. Okay, so I'm going to start from the surface. I'm going to take it down. Let's hope this actually works. You see, now I'm going down into the structure. This is a slice. And what I'm interested in is look at these babies coming up. Wherever these are, you see, we're going to. This is the ground coupled. See, there's now I'm going right into the rebar. Okay, these lines are going right into the rebar. But what I'm interested in, and you can see these. What I believe these are these parts, okay? And it's amazing. So I wanted to look at this very closely, So again,
I don't think I can see your cursor when you're pointing at stuff. Maybe you need.
Hey, yes,
a pointer or something, so I can
let's get the laser point. Is that better?
There you go. There.
I've been pointing at everything and not even know we can see. So I apologize for that. But you see now, so let's talk about this. We're now sliced in. We've taken a slice. We've gone down into depth. Okay, we've gone down about 70 mil, 80 mil. Okay, what we can see there's something going on here. See these little notches? We're going to zoom in on them a wee bit closer and see what's going on. There's just little stuff coming out. This is the plan view. We're looking down into the deck. We've gone down. You can see these lines. These lines are the rebar. Now remember, if it was a perfect world, these would be perfectly straight and they would appear, but it's not. The bridge is old. It was hand laid. You can imagine what they did 50 years ago. So it's all over. It's up and down. Not crazy. This is what I had to do. And you can see different intensities. Some you can see very clearly, here you can't. That's because it's a different level. Okay. Now let's go in. Let's keep going. Oh, the laser's working even better. Okay, so I've just zoomed in just to show you what's going on. I want to show you what's going on, so hopefully it makes sense. In the deck, it's taking me a long section. This is a long section through the data. Okay. So you imagine this could be like one side of the bridge to the other. It's gone into one area, sliced it, long section. Orange line represents the surface. Okay, this is the surface. Then we can see resolve there. We see a clear layer here. Okay, then we go down. So what we know from the cores, this is the interface between the asphaltic concrete and the concrete itself. Okay, the cementitious material. Okay, then further down we've got the rebar. You can see that, and this is me using the examiner going in and taking this slice out. It tells us where I am. It's all very, very good. Wherever slice you take, it guides you. Because you remember, you might have 24 channels. So you're looking at one particular channel of data. And again, you can resolve that. You can look into that. Now look very carefully at this. You can see, I want to get right in here so you can see this. Let's get the laser. Can I turn the laser on at the same time? Yes, I can. Oh, no, I can't. I can't have both, right? Can't point at the same time.
Can't zoom and point.
I can't zoom and point. Microsoft, what's wrong? Anyway, where the blue line is, you see where the blue line is, you can see, right? You can see those are the rebars. Now think about what's going on. In order to do what we were doing, we set it up to scan every 9 instead of 8, 9. That was the way the system was limiting us, because just the way we set it up, the speed we're doing. Okay, and as Paul says, you can tighten that. Okay, so I'm not resolving it. Now, here's the crazy thing. You're looking at this and going, actually, better do that. Yes, you can. So understand me, if you take say you had another company, Jesus, or any of these things, they are different. Okay, they can resolve it tighter. But as Paul says, you can resolve this tighter if I go even slower. Let's go even slower and tighten it up and be very clever. So we were trying to we didn't want to be on the deck all day. We couldn't close it, but to keep it open, we had to, there's some compromise. So what I'm saying is, that's what you have to balance, because you're like, if you've got thousands of bridge decks to do, you want to get this right. Understand, if you've got another antenna that can resolve it, it's fine. But these are done at traffic speed, 25, 30. So you have to be careful. And understandably, there's always a cutoff between. There's always, we had to do this pretty quickly. So that's something you need to take consideration. But again, the data's there. So something to think about. Okay, let's have a look at this. Laser pointers come in. So here you can see the railing. Do you see the railing? This is the railing. So there's a gantry that goes in here. You can get in underneath and look at it. That's being connected. And then, as I said, there's bolts. See the bolts? And here, these little circles that plan through, looking down. This is the scan. We're on the ground couple scan. You can see all these little weird things. Let's look at these closely. This thing's amazing. I'm going to try and run this again. Let's have a look, see if I can get this thing to work. Turn off the pointer. I'm going to click this. So now what I'm going to do again is going to show you that again. I'm going to zoom in a particular area, and we're going to go down into the deck. The system can slice, the software does. See, so now I'm going into the deck. Okay, and you're now looking very carefully. Now you see those, look, and now the rebars are appearing. So I'm down to the depths of the rebars and stop. Okay, so something that's very interesting going on. Okay, and we're going to have a look closely. Again, we'll run again. You see, as I get closer and closer, you'll see these are just the bolts are just sitting in here. We didn't get right up tight again, so we have to be careful. We didn't go right up tight up. So they just about appear. Now, this is where it becomes amazing. Okay, so this is now a long section. So you see now we've got the cross section. Okay, the pan section looking straight down. Now we're doing a long section. This is what they look like, and this is amazing. I'm sorry, I know I need to get out more. This is wonderful. The way it's resolved. Look at the way it's resolved. Like, it's interesting. You can see the mathematical shape of the hyperbola, and I could go into. I'll explain to you at some other point. I'm sure about why it's doing that. Basically, you imagine this, right? I'm going to try and do this with my hand. So here it's scanning here, okay, and it's 3-dimensional scans. Be careful. But what it does is it picks up the rebar. This is the rebar. So what it says is there's the rebar, but it thinks the rebar is closer, directly below, so it's further away. As I move the antenna closer and closer to them, directly above, see the hyperbola comes up, hits this peak. Here we are now, closest point. Now I move the antenna further away. The mathematical shape changes. So now you're getting further and away from this rebar. It's this way. Okay, but it looks like it's further away. And that's you get this mathematical shape. Sorry if that's an awful explanation, but that's what's going on. And here, if you look very closely, it looks to me like there's 2 objects it's picking up. I've given you a hint. We know what they are. Okay, 2 objects. Let's have a look closely at what's going on. Okay, we've gone down into the deck, so let's think what we're looking at. We can see this is the air launch system. See, this is what was amazing with this project. We had an air launch, and it was coming into its own with a ground coupled. Each one is amazing. We were fortunate. There's a lot of money. This is a lot of money having both these systems, but it was great. Helped us. Orange line is the surface of the bridge. Then we're going deep into it. So let's think about what we're seeing. So there's the orange line. That's the direct air coupled. Forget about that. Here, look at here. Now we're going in. You can see it doesn't resolve as clear, but it's good because we were lucky with both. And then we go down, and just where that peak is, that's asphalt, and then that is the concrete interface. This is the different antenna. But again, each one comes to its own. Now what we'll do is let's look at the ground coupled one. Look at the ground coupled one. It gets even better. Sorry about this if anybody's lost a will. But think about what's going on here. Now I can clearly see 2 bolts. The ground couple's even better. It even magnifies it. Just the shape, the way it's ground coupled, it's closer. It can resolve it much better. Now we can clearly see what looks like 2 hyperbolas that are close together mathematically. And it's picking them up. You can see it's got a slight change going on. This system is resolving that. Which is great. So I mean, it's absolutely brilliant. Let's have a look. And so look what happens. The two bolts, the way the antenna screw, because even though, think about this is what's more amazing. We always know about the direction, polarization. Think about what's going on. In standard systems, direction of the antenna, the dipole position, means that normally if you're running, so if I was running a standard antenna from this point to here, we would, and there was a rebar, say it was a bar here, you would resolve that bar.
Your clicker's off. Your
Oh, it's a clicker off. Oh, I've done it again. Thank you.
That's all right. That's all right.
So imagine you're going from here to here.
I'm clicker control.
Oh, that's what I want to do. So imagine we're going from here to here. Okay. If there was a bar here in the old systems, right? In the systems someone says we have, not their old system we're using, on a standard impulse system, you'd walk along here, you would resolve this bar. But if the bar was running this way, you couldn't resolve it. But think about it. This antenna has got antennas going both directions. So therefore, even though the bolts are running this way, you'd think in the old system, is it really going to see it? Because it should be in line. But the way the antenna setup is, the way the dipoles are set, it can resolve it because it's got both, it's covering both directions. So now we've got an antenna system that's got multiple frequencies. And now that the way the dipole shapes, we can see stuff in different directions. And when you build, remember, I'm only showing you, think about this, I'm only showing you a slice, a single slice. The great thing is we can build this into a big three-dimensional model, so you can tell. Okay, so hopefully that makes sense. I know I might begin. And again, the measurement was amazing, and I did a measure. So what I did was I went and measured the position of how I sat on it. I measured the position of the bolt and checked that, and was bang. Oh, it's just, you know, it's just great for me. It was wonderful.
And the collection speed you touched on earlier. Did you say 30 miles an hour?
Yeah, about 25 to 30 maximum. We slowed it down in this one. Because of that dwell time, the more you, so the key thing is you get that dwell time right. It's dwell time. I'm sure Jacobo's going to get me the number. I'm sure it's picoseconds, not milliseconds. Anyway, so crazy thing, just so you all know, the time is measured in nanoseconds per down here, but the dwell time is in. Well, we'll try and get that resolved. Is it milliseconds or is it picoseconds? If Jacobo can write something there, or tell me, or somebody the technical. But I think this is what's amazing.
Yeah. So one of the things that happens with dwell time is since we are stepping through frequency, hence the name. So we're moving through small steps. So the time window that you choose would be traditionally something that you would say, okay, I want to focus on a certain depth. The time window also affects the size of the steps. So in our system anyway. So if you have a larger time window, your incremental step between each frequency, let's say from 100 to 3000, will be smaller. If you make the time window shorter, then your jumps will be more like 20 megahertz steps instead of something like 4 megahertz steps. Okay, so you get a richer response if you have a bigger time window. With the dwell time also dictates how long the system will sit on each of those steps, and they overlap. So it is a little bit like opening a little bit like opening up an old camera and letting more light in. You're kind of observing longer on and dwelling on a frequency for a longer period of time. So if you increase this dwell time factor, then you will absorb more of each of the frequencies as they move through the spectrum. So it's a quality parameter that you can take advantage of with this system. Yeah. Yeah.
Thanks. No, that's really helpful because for me. So as you can see in this particular picture, I've sort of gone in and shown you where these marks are. So these are the bolts, and then sort of show you the breakdown. So it's all measured up. Okay, and it was resolving to these, and you can see there is an air gap here. So you can imagine this was asphalt was laid on this. This is being hand dug out. So, and that's why we had a change. So we go back. That's why we get these weird steps, because again, the antenna is seeing it. You see that we get the wee risers going on here. And just the interaction with different dielectrics, air going faster through the air, so it looks closer. Oh, it's I could go all day about this, but I'll stop. I need to move on to show you some other stuff. So listen, one of the things that we had to do was we needed to guide the team that was going to start taking a Virkin plane and cleaning out the material. They wanted to know accurate depths, and the system was able to resolve these. You can see there was 9 trial bits done. We needed to feed through them the exact depths to plane, so they didn't strike the concrete, and the system was able to do that. And for me, it was weird because some of the deck appeared to be really, really thin. I don't think they believed me, but when they came out and said it was right. When I give them the data, I made sure it was just a few mil high so they can then hand remove, machine remove, not use a planer just in case they struck things. Because again, these are bridge decks. We have to be careful of the damage we do. And that's where it came in. Now, you're going to ask me, I know you're sitting thinking, what is the accuracy? So in the UK standard, the accuracy of radar is about 6%. Okay? What does that mean? If I have 100, I would talk about it in European wise, if I have 100 mil material, then we should be able to measure within plus or minus 6 mil of that. Okay, and that's where our accuracy should be. Now, I would say in this one, it could be a bit accurate, and I know some of you will say, listen, I've got even better accuracy. And I know with this, it's a bit better, but that's the normal range we're working. Okay, 6% is really good. Okay, but I know for some people think 6% is a lot. So again, the more information you have, we're resolving it, the more accuracy we can get. That's where we are, and I was happy with that, and they were. So let me just show you something else that went on in this that is amazing that we didn't realize. This is an area. Remember, I told you about the toll. Okay. When we were doing the scan, we picked up this very interesting pattern. This is the plan view looking straight down. We picked up this weird, so you can see the normal material here just looks, we've gone certain depths into 20 mil, 20 mil. But we're getting this weird looking blacker, darker response, an anomaly. Now, I recognized what I was seeing, but the company that was running the bridge said, I don't know. I thought it was wire. I thought it was some electrical wire. Why would electrical wire be in a concrete bridge deck? Okay. So, but I said, listen, I recognize that. Here's now what I've done now. I've gone closer in. So I've used, this is the air launch material. And I've gone in. You can see this is the plan view looking straight down. You've got this weird looking pattern shape. This is the long section view. Something is going on here. We took some cores around here. Right. Here's an interesting one. Let's look at what the drawing said. So this is a drawing from the 1960s. And we saw this one. Now, the client didn't realize this, didn't know anything of this. The radar did. So let's look closely what this drawing says. So in it, it says inches, great. So it's in inches, and it's much easier for everybody to understand. Probably 2.5 inch, okay, asphalt. But this may be increased required for the heating cables. The radar system now had picked up something that they didn't realize was there. Now, that's a very important thing because the last thing a Virkin planer wants to do a 210 FI, which costs a lot of money, is get metal cables wrapped around the drums. They're not going to be happy. The radar system picked that up. So look very closely. Let's get in here. I've got the pointer. Do you see here? There's a cable. So you see very, very thin. The system's resolving. These black lines are these cables. See, just I need to get the pointer.
You're running with the antenna, longitude.
Yeah. Amazing.
Nice.
So we're running in the direction, and the system is resolved that. Remember we told about the dipole positions? Oh, this is what I want. Now, what's very interesting, see the way we can see that they cut out bits. See the way they've removed bits in the years that have gone past. Just cut them out, didn't even know it was there. Oh, just dig that out. You know what I mean? But the system said they're there. Again, it was great. Okay, it's just amazing. And I can see here, this is it. Sorry, I hope this is some sort of interest. Here's the joint system. I want to show you some, we're getting closer to the end, but this is some of the joint system that's going on. This is how the joints work. It's a mystery to me. Those of you who are bridge engineers should understand exactly what's going on. So you can see the sort of buried joint, some sort of rebar position, and this was going on. We know with bridge decks, and those people who are on this call, we know all about bridge decks, know there's always weaknesses at the joint. That's where the weaknesses are. What I wanted to look at was how well could the radar system pick up condition? And I'm going to show you stuff. It's amazing what it can do. It does take a lot of time, a lot of analysis. So, if client side is listening to this and going, oh, it's great, get this in. be patient with the teams who are working on this. The reason why they may charge you a wee bit more is because it does take a lot of analysis to get this information out, but it's absolutely amazing what comes out. I'm going to show you something.
That is a very good point.
Yeah,
That's a very
yeah.
good
So
point.
please, yeah. So you
Especially
can see
with
this,
bridges as well, right? Bridges
yeah,
are incredibly detailed, right? And
they
there's
are.
no two alike. So yeah,
No,
you are
So,
uncovering an awful lot of information. Yeah.
yeah, and you can think about it. You can see there's something going on. Water's getting in there. You see it's popped. So you can see that this particular shape, the way these joints work, might be a Moira joint. This is a different type of jointing system, whatever it is. And anywhere, those people are listening on this call, from wherever you are, you know what your joint system, and you know there's weaknesses in there. That's just the way it is. It's a challenge for those pavement engineers and structures to try and, that it does take time. So let's have a look at this. You can see this. We did do video runs. So just so you know, there was lots of survey data done. Not only did we do radar, we had video runs, and you can use an examiner to run the videos. Well, we have a separate system, and this stuff that you'll do in GoPros all can be fed in. So not only do you have your radar data, but you also have your video data. We then had people with survey stations, Leica systems, Trimble systems, and they were doing levels. In fact, you'll be amazed at this. When they were doing the surveys, they were doing it during the day. But unbeknown to anybody, understandably, when you've got a survey system, you're resolving to millimeter accuracy, very, very, small amounts of inches, whatever is micro. And the problem was, because of the wind and the exposure, this bridge deck was rising and falling by such an amount. We couldn't physically see it, so the survey team had to wait till the evenings, get the traffic off it, make sure it was quiet, to measure much more accuracy in the survey. That's just getting the detail of every joint, every position. So again, as you all will know, is when it comes to surveying the bridge decks, understand getting maintenance ready, there's a lot of work that goes into it. But once you have the detailed model, we've got the detailed model now, it's going to make it so much easier. The great thing about the examiner is you can then feed in the exact details through your DWG, your CAD drawings, get all that information, and then the radar data can hang off it. That's what you want. And positional, very accurate positional information. So those are the key, and we were fortunate to have that very accurate position information. We then got the RTK correcting, 15 millimeters, very good corrections. That all helps. Okay, and you can correct the data. I'm not showing you in detail. The teams will show you the examiner stuff. You can correct. If you know what's really funny, when we did the surveys, we used the joints to line up the data sometimes because it was just slightly off, and that just happens. But again, because of the joint, and we had this survey data, we could correct things like that. Again, the more you gather, the more detailed information you gather, the better. And as the key thing is, for those on the client side, it does cost, but for the small amount of money that you're paying these amazing companies doing all the surveys, look at the detail you're getting. It's better to get it right now before you open up the deck and go, why didn't we see that? And you're like, well, I told you if you'd used this and you hadn't, don't cut corners from bridges. We've seen the issues that we do cut corners, and we know there is issues in the bridge decks. So let's not cut corners in that. Okay, so this is going on. So this is bad. Around this joint, we see cracks. What does that mean? Water's going to get down into that. If water gets down into that, let's think about it. In the world of radar and water, oh my words, let's think about it. We take standard radar system. We've got 1 for air. The dielectric of air is 1. The dielectric of water is 81. For road materials, pavement materials, everything fits around about 1, 2, 3, for up to about 8, 9, 10. Okay? Dielectric. Water 81. So if you've got water in there, you're going to see a change. Let's have a look what's going on. Change. Now look carefully. This is what is amazing. What you can do, because remember, system, the data is gathered in the frequency domain. This is what's amazing. If you take the standard systems, with the impulse systems, it's all done in the time domain. Then you do Herbert transforms, you go into the frequency domain. The amazing thing about this thing is it's all gathered in the frequency, and then it switches it into time. One day I was speaking to Paul, and I was saying, Paul, Paul just said to me, I'm going to show you a wee trick. Go into Examiner, just switch it to the frequency domain. Oh, that's me. You know what I mean? I was just the whole night, and then I was doing this. It's just great. Sad. And watch the difference. Watch the difference between the poor joint and the good joint. Now here you can clearly see it. Look what's going on. It's just amazing. On the good joint, we don't see the water. That's the water getting in. Look, it's getting right in there. Now, somebody might say to me, and I'm resolving this really tight. Let me just show you what's going on here. I'm getting right in here.
Look, these are into, look, half a meter between these. This is really tight, and I have to really concentrate when I'm processing the data. That just takes the time. But I was able to, discussions with the client side saying, listen, one of your joints is gone. Now, unbeknown to me was he'd gone in, and since the survey, he'd replaced it. He'd said we'd picked up there was an issue. But what I was able to then do is able to say to him, in some cases, some of your other joints are looking a bit dark. He knows it. But again, this is the great thing about the radar system and this data. You're able to see, listen, maybe have a look at this joint. This is what we want. This was a brand new joint. You put a brand new joint in, and I went and picked out this data. Clear. Don't worry about this. This is, so just so you know, and I know it's a bit strange, surface of the road. There we've got the interface layers. Okay, I've changed the frequency mode. Then you've got the rebars, okay, inside the concrete slab. And down in here, you're going right past it. The slab's not that thick. These are like cantilever, the bars, the metal bars underneath the deck, okay? Okay, so don't get confused with that, okay? The main area that we were looking at is here, okay? And it's pretty amazing. Okay, so if we just come back out of this, okay? So let's go, we went onto the job, and look at, I mean, somebody would say it was pretty obvious on the surface, but again, when you've got subtle changes, when they took this away, this is what they found, all damaged. All these bolts and connectors, all water was pouring into them. That's why we're getting this large amount of water getting in, the change, the system's picking that up. Again, they were cutting this out, fixing it. This is a temporary fix because they were going to do real. But here's the most amazing thing. Now, what I'm going to do is try and turn about this out. So this is looking long section, right? So this is a long section, right? So I'm now from there to there, it's me looking from there to there. Now, see these bolts, and it's bolted down. So the actual, keep me right in this one, for those who know, the way the joint's in, I think it's bolted down into the deck. And you can see the system, I know we've gone right in here to the detail, but it's resolving this. This is the air launch system. We can see reflections from these bolts, and you can see there's metal and stuff. There's a lot going on here. You can see they're slightly higher up. You see the bolts are raised up into the asphalt. And I'm going to look at the plan drawing. So the bolts are going up inside into the asphalt, okay? And again, it can resolve it. Now, the challenge is, as I say, I went into nth degree of detail. I sat, it's like I don't know, and just was looking at detail because I wanted to see what was going on. And it was very clear that the data, it was in the data, but you had to look very carefully. It takes time. It doesn't happen. And for those radar teams who are on the call, know that. Therefore, again, it does take time, but it's worth it. And what they can pull out of this is amazing. Okay, listen, we're at the very end. What can we say? GPR has changed so much over the years. From when I was doing it in the early 90s to now, it is amazing. The array antennas, these array antennas are great, especially in the bridge decks. Look at the conditions. It's a really powerful tool. And I can't persuade you enough to say, have a look at, get teams in. There's people on all the different, wherever country you're from, there's lots of teams. You've got these antennas, get them in. You'll be amazed what they can do. Get them in for trial. You will be amazed. And again, listen, thanks so much. I want to thank, there's a lot of companies who've been involved in all of this, the actual contractors, CTM companies that did all the traffic management, PTS for they brought along, thanks so much. Matt tested a lot of testing. The Tay Road Bridge, listen, it's their bridge, and then for WSP. And I'm now going to give it questions, and I think, do I pass over to you, Paul?
Yeah, absolutely. Yeah, thank you so much, Michael.
Yeah,
honestly.
no problems.
The
no problems at all.
There's a lot of interest around radar. There has been that, for many, many years, and this intensity and interest is growing and growing, right? And but it's so important to see this in context and to see real life examples. And sometimes they can be a bit few and far between, so the opportunity to see this bridge, what it looks like with the radar data, then what it looks like when it's been excavated is so valuable. So we really appreciate it. And hopefully some of the attendees also agree with me on this one, because it's quite hard sometimes, especially if you're a practitioner, sometimes you just don't get to see the end result. Right, you sometimes hand over information and you never get to see it. So it's really important to see this in context and to appreciate that this stuff is resolving some real engineering changes, right? Some things that are we don't necessarily see on the surface without damaging the bridge or other asset, right? And yeah, it's great. Have a responsibility to look after what we've built and these kinds of things. So it's really very, very nice. So we really appreciate it. We are we are a little over time. We will, if there are any other questions, there's one question here actually we'll grab just quickly, which is about checking the data for the rebar for corrosion. Why didn't you go down that route? Did you go down that route or anything for looking at the oxidization of the rebar layer? Did you look at any of that, or why didn't you? Did you need to?
Yeah. So our main focus was looking at the asphalt layers, the thickness, and then looking at some of the challenges around the joints. Now, you're totally right. We haven't done that, but that's something that the works will start next year. So it's something that we should be looking at. So we'll go in. How easy can it do it? Listen, think about what's going on. If we take the standard bar within the concrete, if we have oxidization going on and we've got damage and we've got attack going on, we should start to see water must be getting in. Therefore, you're totally right. There will be a change. And it's something that, I need to go. Somebody might say, if you were really going down into that, you would have, ideal would have been going even slower and tighten up that spacing so you could really resolve what's going on in there. I'll have a look at that. It's a good point. We weren't tasked with that, but something, because once they open up the bridge deck, if you imagine what's going to happen, they're going to take off all the asphalt concrete. Then what they're going to have is a specialist team in who's going to get sort of down to level, and then they'll fix. They will have.
Right. If you can, of course, do these kinds of tasks in Examiner, by the way, for anyone that's interested in that kind of approach. We have a customer that's very, in fact, he's one of our distributors in China. And I think it would be interesting about this one. What was the speed of the air launched antenna? Do you know? In this situation.
All of the antennas were run at about 25 to 30 mile an hour. They were all run at that speed. We kept it slow.
Gotcha.
I wanted it as slow as possible.
And hello, John, by the way. I hope that answers the question. I think we should stop there, but we will come back and answer the questions. I hope you found some value in today. It's been very, very nice. I'm going to share my screen if that's okay. Yeah. And tie this up, and also just cover what we're going to do in the next success story, which we've got coming up on the 26th of May. This is going to be with DGT Associates, where we'll have Michael Tuhig and his team with us, which we are super pleased with. We are going to be talking about their use of Kontur and subsurface utility engineering. That's going to happen on the 26th of May at the same time as today's session. And lastly, just to get in touch with us if you have any further more in-depth technical questions, sales-related inquiries, of course, all those kinds of things, you can reach out to local distributors or directly to us, and we'll push you in the right direction. If you want to look at Examiner yourself, then come and speak to us, and we will, of course, talk about evals and stuff like that. Kontur.tech for information via the web, and follow us on our LinkedIn channel to stay up to date. Lastly, thank you so much, Michael. It's an excellent project. Loads and loads of brilliant finds in there. I mean, I love the heating. I love the heating stuff. I love the joints. I love the tiny little bolts on there. I mean, so much in there to talk about and think about. So thank you so much for joining us. It's been brilliant.
Yeah, no problems at all. Thanks so much.
All right, we'll see you next time, everyone. And thank you for attending. All the best. Have a great weekend. See you later.